Good morning. 그 뒤에 앉은 학생들 TV 보이죠? 네. 좀 잘 안 보인다 해가지고. So let's briefly recap what we learned in previous class. So basically we studied some matching algorithm. Why we learn 어떻게 하죠? So why we learn matching algorithm? Let's briefly recap what we learned in previous class. The goal is to understand what is happening in images, but there were some discrepancy between captured images and real 3D world. So it is a little bit hard to understand what is really happening in 3D world because of this kind of vanishing point discrepancy between image and real 3D world, and there are lots of some distortions in images because of the perspective distortion. So the early computer vision, this is just my personal thoughts, tries to understand what is happening in images by reconstructing 3D world from images, because once we recover 3D worlds, we are free from such distortion in images, so that it might be we could understand what is happening in images better because we are free from such kind of distortion. So the early computer vision tried to focus on reconstructing 3D world from images, and the governing theory is multiple geometry theory, which tells relationship between multiplicity observations and 3D space. And the key stuff for the MVG are two things. The first one is camera parameters, intrinsic, extrinsic parameters. We learned this in maybe second class. Intrinsic is for camera to image coordinate system transformation. Extrinsic is word to camera transformation. And then the matching. For the matching, we need to find the consistent point from multiple images, and then we need to lift them in the 3D space, where the consistent means same color dots in images. And we learned how can we get correspondences from multiple images, and this is called matching in previous class. And there were some challenges like repeatability. Where is it? Repeatable. So we need to find some consistent, the same meaning points from multiple images, and then we need to find correspondence between detected features, between detected key points. And there are some challenges like this kind of matching should be invariant or robust to geometric changes, including rotation, scale, viewpoint, and photometric changes, including some affine illumination transformations. And then and we learned very basic stuff. So corner detector is about finding some distinctive feature position. So there are two point features, corner and blob, and we learned very basic corner detection algorithm based on this kind of image gradients. And then we learned how can we automatically select some optimal scale when so basically we restrict our focus on local patches, because in global image there are so many different things. If you see this one, these two are so different. So we only try to focus on local patches, because when we restrict our focus on local patch, we can easily find correspondence. But in local patch, the challenge is finding optimal scale. How can we find optimal scale? Each local patch could have different scales, right? So how can we find scale? Using this kind of automatic scale selection algorithm, we first define function f, and then where f returns the strength of a feature at given scale, and then we find the local extrema of function f, and then so that here. This means that the scale where it has the local extrema in function f means this scale makes this local patch very distinctive compared to other local patches. So we say this scale as a optimal scale for this local patch, and then we hope this scale could produce the same local patch across different images from different viewpoints and different scales. so that we can easily compare this one, easily compare the selected local patches based on selected scales, so that we can find some meaningful correspondence between images from different viewpoints and scales. And then the commonly used function f is a some convolved image where kernel is, the edge detecting kernel. We can predefine some kernel, and then we can just do convolution to make function f, and then just retrieve some pixel value from this convolved image. F becomes just a function f. And then Laplacian of Gaussian is widely used for this purpose. So, and we learned some Hawk. And the shift, this kind of lookup patch, this kind of automatic scale is based on some position, right? We need to first define the position of this local patch, and then we find scale, right? The position, how can we find position? How can we define position? The position is decided based on this. Maybe we can use corner detection algorithm to localize corner, and then we can select some optimal scale from localized corner. And then where is it? Yes. And so we use some automatic scale assignment algorithm based on Laplacian of Gaussian, but it's slow. And there can be multiple local extrema, which makes it unstable. Rotation assignment, we use dominant orientation, but not robust if multiple rotation patterns extend the patch. And affine invariance, we used Harris eigenvectors, not robust to large viewpoint changes. So that motivated us to study shift in last class, and we are now start to study shift. Shift is a short term of scale invariant feature transform, invented quite a long time ago, right? 20 years ago, from David Law. He's at this moment professor at University of British Columbia, and as you can see, the citation number could depends on which community you are going to study, but this citation number is quite huge, about 68K. This is very huge, and still widely used. Shift is very seminal work in computer vision history. So this shows a nutshell to compute shift descriptor. Descriptor computation, we consider 16 by 16 pixel patch, which is a local patch, right? We are not going to see entire image. We only see local patch from entire image. And then we multiply patch by a Gaussian filter. Gaussian filter means like a Gaussian, you know Gaussian, right? This is Gaussian distribution. So we can, usually filter means like a 3x3 or 5x5 filter. And then this is just two-dimensional Gaussian. This one might be 1, maybe 0. So Gaussian filter is like a 3x3 filter where maybe this one has the largest number, and this one might be a little bit smaller, and this one even more smaller, maybe. Just a random numbers, but this kind of filter is called Gaussian filter, which has a similar shape with this Gaussian distribution. Applying Gaussian filter makes the images a little bit blurry. And then so we apply Gaussian filter and compute dominant orientation and de-rotate patch. And we compute Hawk descriptor. We learned Hawk descriptor in previous class, right? It's kind of computing some gradient in pixel space, RGB space. To compute Hawk descriptor, Hawk means histogram of gradient. So that means we need to compute some gradient, right? From computed gradient, we can make histogram. Histogram is just a, histogram, just a graph of some frequency. Maybe there should be some gradient, range of gradient, range of 1, range 2, range 3, and then we can find some dominant range of gradients from this image local patch. It's just a brief visualization of Hawk. So we compute this Hawk descriptor, divide patch into 4x4 cells, as you can see here. This is image gradient, and then we divide it to 4x4 cell, Here we can see 1, 2, 3, 4, 1, 2, 3, 4, right? 4 by 4 cells, and use 8-beam histogram. B means direction. So when we compute gradient is just a direction, right? And we predefine 8 directions. 8 means like then we have 8 directions, right? 1, 2, 3, 4, 1, 2, 3, 4, 8 direction. So we to make histogram, we predefine 8 directions and concatenate all histogram into a single 1D vector. That makes 128 values, resulting in SIF descriptor 4 by 4 from these 4 by 4 cells, and 8 for each cell. We have 8-beam histogram, right? So 4 times 4 times 8 becomes 128 values. That is key point descriptor, SIF descriptor. We can call anything. And for the matching, we need to compute similarity between SIF values from different local patches to compute how similar to local patches. We compute SSD, sum of squared difference. We learned this in previous class. Just the Euclidean distance between local patches. And there are some numbers, specific numbers, right? 4 by 4 cells, 8 directions. We will justify why we use 4 by 4 cells and 8 beams when we compute SIF descriptor. Just based on, just the short conclusion is just based on some experimental observation. The author, David Lowe, he tested multiple combinations of the size of the cell and the number of beams, and he found that the combination of 4 by 4 cells and 8 beams works the best for majority of images. So he just said 4 by 4 cells and 8 beams. We will see this later. So anyway, this is just a very brief description of computing SIF descriptor from images. We consider 16 by 16 pixel patch, and then we apply Gaussian filter, and then we compute Hawk descriptor based on this kind of specific numbers for 4 by 4 cells, divide patch for 4 by 4 cells, and then use 8-beam histogram, and then just compute the gradient. That becomes 128 numbers. That is the how we compute SIF descriptor from local patch. And after computing this Hawk descriptor, we do something more like normalization. The Hawk descriptor is already invariant to additive elimination because it is based on gradients. Invariant to additive elimination means, so we learned invariant, right? Invariant means the function, invariant means maybe this one. Regardless of, so the function f is invariant to function g. We can call, yes. The function f, the return value of function f is not related to applying any transformation function g. This is invariant. And invariant to additive elimination means maybe we can bring maybe we can add some constant pixel values, pixel offset to the local patch, right? So for example, if we have this 16 by 16 local patch, we can add scalar, like maybe 10, to make it brighter. We can add number 10 to all the same pixel offset to all the pixels in local patch, but gradient is the same, right? Regardless of which scalar we add, the output gradient is the same. So that means it's invariant to additive elimination. Regardless of which number we add for the elimination changes, like a number 10, plus 10, minus 10, plus 20, minus 20, the gradient is the same, right? So the Hawk descriptor is already invariant to additive elimination. And additionally, to make it invariant to affine elimination changes, the descriptor vector V is then normalized such that L to norm is 1. For example, high contrast photos could linearly increase gradient, right? High contrast means darker region becomes very dark, and brighter region becomes very bright. High contrast photos could linearly increase gradient, right? The darker region becomes very dark, and brighter region becomes very brighter. then the gradient becomes larger linearly. So we make the descriptor invariant to such changes by normalizing it, so that the L2 norm of this descriptor becomes 1, so that we can make our descriptor, SIF descriptor, invariant to not only additive elimination, but also affine elimination changes. I mean, additive and affine are different. And we can conclude that SIF descriptor is invariant to affine elimination changes because the Hawk descriptor is already invariant to additive elimination, and also we make it invariant to elimination changes. So let's clarify this again. So affine elimination changes, we learned this in where is it? We learned this affine elimination changes. Yes, here. So this is affine transformation of elimination, right? Alpha image plus beta. There was affine elimination changes, and then let's get back to this slide. Okay. So alpha I plus beta, and plus beta is already invariant to plus beta because the Hawk descriptor is already invariant to additive elimination changes, right? So our SIF descriptor is already invariant to this plus beta term, and multiplied by alpha. We normalize it, so the alpha just cancel when we normalize it. So the alpha I plus beta, this kind of affine elimination changes, our SIF descriptor is invariant to such kind of affine elimination changes. It's plus beta, already invariant, multiplied by alpha. We normalize it, so the alpha is canceled. So our SIF descriptor is invariant to both additive elimination changes and affine elimination changes. Actually, affine elimination changes include these additive elimination changes anyway. So that we can conclude that SIF descriptor is invariant to affine elimination changes. And so this is this example is the first example that I showed in the last class, right? This is actually from SIFT. SIFT matching robustness can handle severe viewpoint changes up to 50-degree out of plane rotation. Can handle even severe non-affine changes in illumination, low to bright scene. So you can see this is quite bright. This is quite dark. I'm not sure these are available at this moment, but you can try this. And SIFT is integrated into OpenCV C implementation. And so there's a specific number, 50 degree. 50 degrees just from its paper. The author did some experiment and they found that up to 50-degree viewpoint changes, the SIFT descriptor works quite well, quite robust. So this is just a experiment based on experimental results. And in last class, we used Laplacian of Gaussian, right? But it turns out the Laplacian of Gaussian is too computationally expensive. So instead of using Laplacian of Gaussian, SIFT descriptor uses difference of Gaussian. So difference of Gaussian is just from its name we can know that just a difference of Gaussian. We apply Gaussian filter, just a Gaussian filter using different standard deviation. That means, I said applying Gaussian filter makes the image a little bit blurry. So this is just a pixel-wise difference between images from Gaussian filter with different standard deviations. Just a pixel-wise difference. And based on this kind of, I'm not sure, I'm not very familiar with this heat equation, but based on this heat equation, it turns out that Laplacian of Gaussian can be approximated by a difference of Gaussian, so that we can, and difference of Gaussian is computationally much more cheaper than Laplacian of Gaussian. So SIFT descriptor decided to use this difference of Gaussian instead of Laplacian of Gaussian. You can see this visualization, a little bit different, but we can approximately say that the difference of Gaussian could be used as a trade-off for the computational cost. And let's see this one. So there are actually SIFT descriptor. We need location and scale. It is similar to what we learned in previous class. So we need to find local extrema in both location space and scale space of difference of Gaussian images. So this shows some actual implementation. Each pixel, so let's say we have some image. Local patch, and then each pixel is compared to 26 neighbors. Here, the black cross is the current pixel, and there are 9, 8, 9. Summing them becomes 26 pixels. So the black cross pixel is the current pixel, and we compare the black cross pixel with the remaining green circle pixel, where the number of green pixel is 26. 8 neighbors in the current image, this one, 8 in the current image, and then 9 neighbors in the adjacent upper scale, this one, 9 upper scale, and 9 neighbors from the adjacent lower scale, this one. So that makes 26 neighbors, and compare. So we always compare a pixel with the 26 neighbors, and if the pixel is the global maximum or minima, that means extrema, right? Respect to its 26 neighbors, then it's selected as a SIFT feature. So for each extrema, the output of the SIFT descriptor is the location, this pixel's location. We know this pixel's location, right? Location and scale. So there are multiple scales. We will see how we can build scale space later. There are multiple scales, right? Let's say scale 1, scale 2, scale 3, scale 4. So this image belongs to scale 2, right? And let's say this image pixel position is x, y. Then it turns out that this pixel is the extrema in local, comparing 26 neighbors, and then we can say that we can save this pixel's position, like position and scale S2. This is S2, right? So this is how we compare each pixel with the 26 neighbors, and then getting position and scale information of that pixel. And let's see an example. So this is visualized DOG, difference of Gaussian images. Here you can see. So once we apply, as I said, once you apply Gaussian filter to image becomes a little bit blurry. But here K sigma, we have K sigma and sigma, right? That means we apply Gaussian filters from different standard deviation. So let me clarify what different standard deviation means. So let's take an example of 3x3 Gaussian filter, and maybe K sigma and sigma. So the standard pixel might be 1, 1, but maybe this one 0.7, 0.7, 0.7, 0.5, 5. This might be K sigma, but maybe sigma is just like 0.5, 0.5, and 0.3. So we can use different kernel, and then just apply this kernel, just apply convolution, right? Convolution with this kind of different kernels. So that, and then we get difference for each pixel-wise difference. So subtract each pixel, so that we can get this kind of some image. This is just a literally difference between Gaussian. And so as you can see, this is a little bit interesting. So this is real original image, and this is DOG. As you can see, these background pixels, pixels without distinctive texture patterns, they do not have any activation, just black here, black, and but some pixels, some positions with distinctive texture patterns, like this kind of patterns, I mean, where gradient, this magnitude of gradient is a little bit big, if the magnitude gradient is a little bit big, then such points have some activations, right? And now we are trying to use different scales. I mean, in here we use k sigma and sigma, and here k square sigma and k sigma, k cubic sigma and k square sigma. So we keep doing this to get degree of Gaussian images. Example. So as you can see also this one. This, as you can, if you change the slide, you can see the size of the difference of Gaussian becomes a little bit bigger. And we haven't learned octave, but let's go to this. I mean, anyway, we will study what octave means. So anyway, so as you can, if you see this one, you can see that images becomes more and more blurry and more try to find some big local patches, big texture and patterns. So here, the first one, it tries to detect very fine texture and patterns, very small scale, fine scale texture and patterns here. But then if you keep going, then now it tries to find some very big patterns, right? There's no fine details. There were fine details in here, but from this scale, we can't recognize any detailed texture and patterns, only very rough texture and patterns, big scale and big rough texture and patterns. So this shows visualization of SIFT. I mean, we from the difference of Gaussian images, we find local extrema, and then we did the same thing. We learned this here. Here. So for each extrema, I mean, we compare each pixel with the 26 neighbors, and then we decide whether it's a local extrema or not. And then if it turns out local extrema, we store position and scale, right? And this is just a visualization of position and scale. Each circle, I mean, center of circle means position. Center, x, y. And radius, sigma. Sigma means the scale that this pixel belongs to. And sigma is just the standard deviation of the Gaussian filter, right? So by comparing each pixel with 26 neighbors, we can save center of the position of that pixel and then scale of this pixel. This is a visualization of detected combination of center and radius. The center of circle means position of the point, and the radius of the circle means just the standard deviation of the Gaussian filter. So that we can, as you can see, there are like if there's a very small detailed texture and patterns, the size of the circle is very small, like this kind of. Let me change the color. You can see here, the size of the circle is very small when there is a very small scale, fine, detailed texture and patterns. And as you can see here, like if the texture and pattern is very big and like a coarse scale, then the size of the circle is big. So this means that SIFT can somehow automatically detect scale of local features. And of course, it's not very perfect, but this gives enough information to find some good correspondence between images from multiple viewpoints, and it only based on RGB pixels. It's really surprising. So some distinct points can be extracted from difference of Gaussians. Local patches without distinctive texture should not have big difference, right? As we see here, all the entire background pixels, they do not have any activations, right? So they do not have any activations. Pixels with some distinctive texture and patterns, they have this kind of detected features. And as I said, for the visualization, we draw a circle at the position of the local extrema, where the radius of the circle is from selected scale. Actually, in addition, we can find dominant rotation. Actually, we didn't include dominant rotation in this visualization, but as I said, we draw a histogram, right? Histogram of gradient. Then we can find a dominant rotation from histogram. As I said, we used Hawk histogram of gradient. Then we can find dominant gradient from histogram of gradient. We can just select gradient where the frequency is the largest, right? Then that means dominant histogram. And then actually we can include rotation as well in visualization. For example, if you find some result of shift features, you can see this kind of lots of circles, or you can see this kind of some circles with some lines. You can see some. If you Google some shift result, then you can find this kind of circle visualized results, or you can find this kind of circle with two-line visualization. This means rotation. This means rotation of local patch. We didn't include rotation in this visualization, but you can also include rotation in visualization, because shift actually includes, we will study this later, but actually shift also provide rotation as well, rotation, theta. This means rotation. For the same circle, we can change the rotation. So actually, rotation is also what we get from shift, but for the visualization, we just did not include it because it can make a little bit messy. There are too many circles. And in practice, how can we implement this? As I said, we first apply Gaussian kernel. Like the initial image is incrementally convolved with the Gaussians. As I said, we just do convolution with the Gaussian filters to produce blurred images separated by a constant factor k in scale space, shown stacked in left column. So these ones are original image. H means height. H, height. W means width. So this is original image, and here you can see this is small g sigma, gk sigma, gk square sigma. So from original image, we apply Gaussian filter with different standard deviations to make images blurry, and then we subtract. This is DOG, right? Difference of Gaussian. This is difference of Gaussian, right? So we subtract the Gaussian convolved images to get difference of Gaussian, the blue one. And here we have, and then here we have octave. Here is first octave, you can see here. First octave, next octave, next octave. Octave means images with the same resolution. All the images in the same octave, they have the same resolution, height and width, or half one. H divided by 2, W divided by 2, H divided by 4, W divided by 4. So each images in each octave, they have the same resolution, but they are convolved with different Gaussian filters, different standard deviations, right? As you can see here. So this is first octave, but there are 4 scale images where each images from the same octave but different scale are convolved with different Gaussian filters, with different standard deviations. So that is some actual implementation of this kind of how can we get DOG. So that means before computing shift, we actually prepare different resolution of images, and each different resolution images are convolved with different Gaussian filters. That is what we prepare before computing shift values. Here, these are just some specific numbers. The initial Gaussian G sigma has sigma equals to 1.6, and k is chosen to 2 powered by 1 divided by s here. Just the empirical founding, where s is number of intervals into which each octave of scale space is divided by. So these are s equals to 4, because there are 4 no, 1, 2, 5, sorry, 5. There are 5 images in each octave, right? So S equals to 5. As I said, each octave consists of S images blurred with different standard deviations. And adjusted blurred images are then subtracted to produce the difference of Gaussian images here, the blue one. So from difference of Gaussian, as I said, from each pixel in difference of Gaussian, we compare 26 neighbors to decide whether this is a local extrema or not. If it turns out local extrema, we store its position, scale, 128 key point descriptor, and dominant rotation. So, I mean, detect local maxima, local minima, which is local extrema in scale, space scales. And this shows prepared DOG images. I mean, so as you can see, this is the same octave. They belong to the same octave, and as you can see, the image becomes more and more blurry, right? Because we apply different Gaussian blurring, different standard deviations, but they have the same resolution, right? Height and width, right? Same resolution. Images in the same octave, they have the same resolution, but they are convolved with Gaussian filters with different standard deviations. This one, H divided by 2, W divided by 2. And these are actual DOG images. As you can see, each local patch, I mean, each DOG has different informations. So here we can find more fine details. Here we can see more coarse texture and patterns. So we prepare all this kind of stuff before computing SIFT. But what we learned in previous class, it does not use DOG. It uses Laplacian of Gaussian, but it turns out that, so preparing this kind of all this stuff, I mean, as you can see, this seems a little bit computation expensive, right? Especially considering this is invented 20 years ago. But Laplacian of Gaussian makes this much more computationally expensive. So SIFT needed to lower the computational cost so that it just use difference of Gaussian. So let's recap. SIFT is scalar invariant feature transform, an approach to detect and describe regions of interest in image, right? This is a little bit ambiguous. We are not trying to find some specific point. We are just trying to find some point which has enough distinctiveness. So this is also a little bit ambiguous, but it just tried, because it is not about specific object. It is not about some specific object. Like it is not only for remote control. It's not about only human. It is for all kinds of CNN object. So this algorithm couldn't define specific set of key points, but based on gradient in image space, it tries to find some distinctive points, and that is the purpose of SIFT. And based on difference of Gaussian and just finding local extrema, and SIFT features are invariant to 2D rotation because we can find dominant rotation from histogram of gradient so that we can derotate it. And then reasonably invariant to rescaling because we can, I mean, as I said, we have octave, and then each octave have different scales so that we can find some optimal scale based on this kind of different set of octave and different scales. And viewpoint changes, as I said, this is just the empirical finding. It is robust to viewpoint changes up to 50 degrees and eliminations. Elimination, as I said, HOG is HOG is invariant to additive elimination changes, as I said, and by normalizing it, it can be invariant to the affine elimination changes as well. So thanks to the DOG, not difference of Gaussian, it runs in real time but still expensive actually. Considering this is invented 20 years ago, it is. I think this is not expensive at this moment. We have lots very advanced computational hardwares these days, but at that time, CPU was dominant device. Now all people use GPU, right? But at that time, GPU was not mature at all. So most of the algorithm runs in OpenCV are based on CPU, and it might be a little bit slower and expensive. Expensive steps are the scale detection and descriptor extraction. And this shows the original demo. I think this is from CVPR 2003, maybe around. As I know, he opened some tutorial in CVPR 2003 and showed some demo. So this shows some demo, right? So you can see it's a little bit hard to recognize, but images from this one and this one, viewpoint is very different. Scale, rotation, all the stuff are really different, but magically it can find some correspondence. And these are some detected key points. It tries to find some distinctive points from images. As I said, so I guess the major goal of this kind of SIFT could finding some correspondence between images from different viewpoints, so that images could be reconstructed to 3D space, so that we can understand what is happening in images better. Because once we recover 3D, then we are free from such kind of distortions. So let me clarify what is input, what is output of this SIFT. So there are 4 stuff. Descriptor, so from 16 by 16 local patch, 16 by 16, we made it to 4 by 4 cells, and then there are 8 being histogram, right? So this makes 4 by 4 by 8 means 128 element 1D vector. That is the first one. And location of this kind of local patch. When we compare 26 neighbors, as I said, the black cross dot pixel, we learned this, right? The position of the pixel and scale. We need to know the octave and the scale for each octave, right? So that we know scale and orientation. We have histogram of gradient, right? We have HOG, histogram of gradient, and then we can find dominant rotation from histogram. We can just pick rotation whose frequency is the largest, then that might be dominant rotation. So these are what we get from SIFT. So in total, 128 plus 2 position plus 1 scale plus 1 rotation. That makes 132 numbers, 132 vector. That might make the final SIFT output. Or this might be 2, because we need to know index of octave and index of each scale in octave. So depending on the implementation, we can maybe scale might be 1 or 2. So 132 or 133. There's no fixed numbers. You can change all the things. You can change this one. You can change this one. You can change all the things. But you need to understand what we get from SIFT. So this is a descriptor. Descriptor means information of local patch, and then location means position of that point, specific point, and scale means which scale makes the local patch most distinctive compared to other local patches. And then orientation means dominant rotation from rotation histogram, because we have histogram gradient, we can get a dominant rotation. So that makes final output of SIFT. We have this kind of 132 dimensional vector from 16 by 16 local patch. So far, good, clear? Any questions? Anything is unclear about SIFT computation? Okay. And this shows some experimental result, experimental demonstration of SIFT. Actually, I think this graph is quite hard to recognize. I think that this kind of visualization is a little bit different from these days visualization. This is just a different story. So this is IJCV, International Journal of Computer Vision. IJCV is just so these days, most of the computer vision researchers submit their papers to conference like CVPR, ICCV, ECCV. These 3 conferences are the primary conferences that researchers submit their papers. But back in the day, IJCV or TPAMI were good journals. So these are conference and these are journal. And So IJCB, so the SIFT is published in IJCB, and so IJCB is now, I mean, people now these days is getting, I mean, these days people are not actually actively trying to submit their papers to IJCB, but there are two very seminal, very famous papers in IJCB, SIFT and ImageNet. Have you heard ImageNet? ImageNet is a image classification data set used in AlexNet or VusionNet. So ImageNet, IJCB, they are very seminal work published at IJCB. Let's get back to this one. So this is very hard to see. First one, we can clearly distinguish, I mean, these patterns. And from this graph, it seems that, so this is the correctly matched one percentage. So it seems only using key point location gives the best choice, but actually it is not. It's a little bit hard to recognize this graph. So key point location evaluate only whether the same spatial position is detected. So it requires ground truth, and I mean just the upper bound of SIFT. I mean it tries to measure upper bound of SIFT-based matching algorithm. So it uses ground truth correspondence during evaluation. So it is not usable in practice, just to try to find the upper bound of SIFT algorithm. Location and orientation as well. So we had all this stuff, right? Descriptor, location, scale, orientation. This one only used location, x, y. Without descriptor, without scale, without orientation, assuming all the stuff are correct, only tries to evaluate the position and location orientation. Assuming all the things are correct, assuming all the things like descriptor, scale are correct, only tries to evaluate location and orientation. So this is also, it requires ground truth, not usable in practice, but it tries to find upper bound of SIFT. Nearest descriptor is in here. This is full 128 degree dimensional descriptor for matching, enabling correspondence without ground truth. So this is real performance of SIFT, nearest descriptor. And so as you can see, these are upper bound, upper bound, upper bound. This is real. When we only focus on position, when we only focus on position and orientation, and when we focus all the stuff without using any ground truth, so this is real, upper bound, upper bound. And from this graph, we can see that the viewpoint angle here, we set 50 degree, right? In previous slide, we set 50 degree. The SIFT algorithm, SIFT matching works robust up to 50 degree. The 50 is from this graph. So, I mean, if viewpoint angle is getting higher and higher, the matching performance becomes lower and lower, right? It is obvious because when we change the viewpoint significantly, it makes more harder and harder to find correspondence between images from different viewpoints. But up to 50 degree, it works reasonably, like about 50%, maybe 50%. Works reasonably up to 50 degree. And here, number of scales per octave. So for each octave, we had the number of scales, right? In previous slide, we have 5. We had scale equal numbers to 5, right? In previous slide. And these ones are the same. This is upper bound. Upper bound. This is real. Matching location and scale, assuming all other remaining stuff are the ground truth. And this, the nearest descriptor in database is the real one. Anyway, and so from this graph, it turns out that using scale as a 3 might be the optimal solution, but I'm not sure the exact reason. I'm not sure the exact numbers that the author used, but from this graph, using only scale equals to 3. That means for each octave, only 3 images are included for each octave. But maybe, and this is the example that we saw in previous slide. There's no big difference, but using scale equals to 3 makes the performance a little bit better than using scale equals to 5. And the interesting thing is that if we increase number of scales per octave, more and more, the performance becomes degraded. Maybe it is too redundant and too noisy if we have too many scales for each octave. So we need to find some good balance. And then influence of orientation and number of stop patches. So from this one, we now justify why we use combination of 4x4 cells and 8 pins. It's a little bit hard to recognize this graph. I think at that time, the papers only support grayscale papers. They were not colored figures, I guess. So that it is a little bit hard to recognize this graph. The graph shows that single orientation histogram, n equals to 1, very poor at discriminating. Here, n equals to 1. Now we use, where is it? So this n equals to 1. And now we use n equals to 4, right? 4 by 4. So n equals to 1 becomes 2, very poor at discriminating. So n equals to 1 means just using a single dominant rotation. So we now 4x4 cells, so we have 16 kinds of rotation, right? But n equals to 1, it only uses a single scalar to single rotation, single dominant rotation to describe that local patch, and that makes very poor. And that makes sense because using only a single orientation histogram do not include any information, useful information, I guess. And here, 4x4, combination of 4x4 and 8 orientation performs the best. So that is the reason why we use 4x4 cells and 8 orientations. You don't have to memorize these specific numbers, but they are just, I just would like to let you know that these numbers are just from experimental demonstration, experimental results. Combination of 4x4 cell and 8 orientation makes the result the best. Let's see the application. As I said, we can use SIFT to 3D reconstruction, getting correspondence from images from multiple viewpoints. But it is not only restricted to such kind of 3D-based stuff. It can be used for other things. Back in the day, object recognition was based on template. So it kind of some getting the same image, finding some same object from database. So we have in database, we have like some template of this book, template of this book, and the roller algorithm is to try to find where this template A, template B, where template A exists. What is the actual position orientation scale of the template A in this image? It tries to find position and rotational template, but using SIFT, we can compare this template and find detected image, so that we can make a correspondence between template and object and image. That is for object recognition back in the day. And as I said, we can use SIFT to panorama stitching from images from multiple viewpoints. Different time step. We can stitch them together, warp them together to make them a long, wide angle image. And remaining thing is a matching. So far we only studied how can we compute SIFT, but after computing SIFT, we need to find correspondence between them. So let's see, we have these pixels. This pixel turns out that distinctive, and these are the detected SIFT features. But there are 4 points, and there are 4 points, and for this point, which one is from this out of 4 points, which one is the consistent point of this point? We need to know that. The basic, strategy is just using brute force matching. We have, n times n, the n square comparisons. And for the comparison, we use this kind of, we can use just SST, sum of square difference, to check whether these two detected points are the same point or not. We can just use Euclidean distance between, we have 128 descriptor, right? 128 dimension descriptors for each point. Then we can measured distance between 120 dimensional vector of this point, 120 dimensional vector of this point. We can, keep changing, keep measure difference between different points and then find the closest descriptor. That is the basic strategy. We can just do brute force matching. Of course, in practice, we often do not use brute force. To make it more efficient, we might use KD tree or other stuff, but this is a little bit out of focus. So basically, we use some advanced data structure or just use brute force matching to find correspondence between detected shift from image 1 and image 2. And for the comparison, we use 128 dimensional vector that we compute when computing shift descriptor. But one thing is that if we just simply pick closest descriptor, so let's say we have 4 from image 1 and image 2 we have, then it turns out that the first descriptor is the shortest distance between this one. Then we can make a correspondence between the first point in the image 1 and third point in image 2, but it might prone to noisy, right? It might prone to erroneous matchings. So what people try to do to address this kind of false match is that tries to consider the second closest descriptor as well. So compute ratio of distance to first to second closest descriptor, and then so D1 is the distance from the closest descriptor, and the D2 is the distance of the second closest descriptor. And that means we additionally consider second closest descriptor when we find the correspondence between different set of points. And if the D1 divided by D2 is smaller than threshold, usually 0.8, then we make a correspondence between when we say this is the good correspondence between this point and the closest descriptor. And this graph shows the SIFT paper recommend to use 0.8. And here, as you can see, this is the PDF probability density function, and this is correct, and this is incorrect, incorrect. As you can see, if the ratio is 0.8, only very few amount of positive matches are ignored, right? So 0.8 is good, and majority of negative, majority of negative samples, wrong correspondence can be prevented, so that the authors recommended to use the threshold on 0.8. It is also based on experimental result. So by considering second closest descriptor, we can prevent false matchings. And let's see applications. Like as I said, object recognition is or panorama stitching. In addition, we can use structure from motion. We will study structure from motion later. This is, I guess, Times Square in New York, maybe. I'm not sure. Anyway, we can scan our scene. We can scan our scene with our mobile phone. We can film a video with our mobile phone, and then for each adjacent frames, we can find correspondence using SIFT. And then, as I said, once we have correspondence, we can lift them in the 3D space, and that makes this one, structure from motion. Based on detected correspondence between adjacent frames, we lift them in the 3D space so that we can recover 3D structure from motion. That is why we call this structure from motion. We can recover 3D structure from camera motion. That is why we say this is structure from motion. Structure from motion, a failure case. Obviously, SIFT only see local patches. So it actually lacks global context. If there is a similar pattern, right, like let's say this one, window detail might be very similar for all the windows, then there can be wrong correspondence between different windows, right? And similar patterns, brick pattern is similar across all the entire region of the house, then it also could make some failure correspondence. That is, I mean, obvious because it is only based on local patches. At that time, I mean, these days, we have lots of advanced data-driven learning-based systems to consider global context when matching. But at that time, we only saw local patches, and that is an inherent limitation of local matchings. And let me introduce some recent works. So these days, people try to do more stuff like it's called semantic matching. So these are different objects, right? Different object, but they might have share similar structure. Like bird, they have face and wing, leg. Cat, they also have them eye and nose. And cars, they have some distinctive point like a light and wheel. Bottle, they have the top and bottom part. All this stuff, they are from different objects, but the people try to find, object from the same category, they could share same semantic meanings, right? So people try to find a semantically consistent point, which is called semantic matching. And more practical stuff is person re-identification. So now it is not about 3D. So this is not about 3D. This is not about 3D. Just so person re-identification. This is target person's image, and then it tries to find the closest person from candidates. And this is a little bit very challenging at maybe 2017, 18 person VID. There are lots of person VID papers at about 2017 or 18, 19. This kind of whole body human or face, anything can be used. Anyway, this is person re-identification. And more recent works actually do something more. It is a little bit different. So it is not about matching, but they try to find semantically good features. Let's say. So these days, people try to use many unlabeled images. Getting labels from all images too expensive and too time consuming. So, but there are many unlabeled images without any labels. How can we use that? There are many images on the web, right? So the first approach, I guess, is the contrastive learning, self-supervised learning, contrastive learning. They try to train visual features without labels. In short word, embed similar-looking images closer in the embedding space. These are dog. These are not dog. So when we try to embed dog images in a similar position at the embedding space, and cat should also be in the similar space. Elephant should be a little bit different space. It tries to embed them into embedding space, and then that is contrastive learning. I guess is introduced in 2018 or 19, and at that time the performance was not very mature. But these days it's really surprising. So Dino 3 is from Meta, very recent work, but maybe less than 1 month, I guess. So basically use much more data and much more advanced neural network architecture, so that it is surprising that these images are from different image, but cat has some distinctive parts, right? Ear or leg. This kind of stuff can be consistently detected without any label, without any manual labels, just using contrastive learning, self-supervised learning, unsupervised learning. So that this kind of visual feature extractor, which is called Dino 3, can be maybe quite useful because it understands what is cat. This cat eye is has some distinctive information, and it is consistent across different images. So it understands the structure of cat, structure of any object, because it is trained on massive amount of training set from massive amount of diverse objects. So it now understand some distinctive parts of the image, distinctive part of object, without any label. This is really surprising. And from this aerial image, as you can see, the street has the same color coded, right? It's really, and the green part also in the same color coded, really surprising. They can find some, correspondence from images, although they are not from the same 3D word. They share semantically similar meaning. Then these days, visual extractor can find correspondence between this kind of images with different 3D object, but share some similar informations. So this, let's finish today. And any question about today's shift and application? Anything is unclear? Good. Let me quickly summarize in Korea and finish the class. 이게 shift 디스크립터 계산인데 뭐 로컬 패치를 쓰는 걸로 저번에 얘기를 했었고, 이게 가우시안 필터에서 이미지 블러리하게 만든 다음에 호그 디스크립터 적용해서 계산하는 거거든요. 근데 뭐 4x4 스타일로 하고 디렉션을 8개로 나눠서 한다는 거고, 노멀라이저를 해서 일루미네이션에 어젝티브랑 어파인 트랜스포메이션에 이제 인베리언트하게 한다는 거고, 중요한 건 이제 difference of Gaussian을 쓴다는 거예요. 라플라시안 of Gaussian은 너무 computationally expensive해서 difference of Gaussian을 쓰고, 이제 한 픽셀당 26개 네이버랑 비교를 해서 이 픽셀이 디스팅티브 한 픽셀인지 아닌지를 판별하는 거예요. 근데 이제 이때 로케이션이랑 스케일을 알 수가 있죠. 이 디퍼런트 스케일이 있고 이 픽셀의 포지션이 있으니까요. 그래서 예시를 보면은 첫 번째에서는 매우 fine detail, small scale 텍스처 패턴들은 이제 recognize 할 수 있고, 그 다음에 점점점 가면 갈수록 큰 스케일의 텍스처 패턴들을 이제 액티베이션이 있는 거를 볼 수 있고, 그래서 보면은 이렇게 큰 텍스처 패턴뿐만 아니라 작은 것들도 다 액티베이션이 돼서 디스팅티브 해 보이는 피처들은 포인트들은 다 로컬라이즈 아이덴티파이를 했다는 거예요. 이제 그래서 얻는 거는 센터랑 레디어스로 원을 만든 거거든요. 원의 센터가 이 픽셀에 비치고 레디어스가 스탠다드 데비에이션이고요. 로테이션은 여기 포함이 안 됐는데 가끔 구글링에 보면 이렇게 돼 있는 거 있거든요. 이게 로테이션이 포함된 비주얼라이제이션이에요. 구현할 때는 말씀드렸다시피 각 옥탑을 이렇게 정의하는데, 하나의 옥탑에는 같은 해상도의 이미지들이 있는데 한 옥탑에 다른 스케일들이 있어요. 가우시안 블러를 다른 스탠다드 데비에이션으로 적용을 한 다음에 이거 픽셀 와이즈 빼서 디퍼런스 가우시안 만들고, 거기서부터 이제 시작하는 거예요. 거기서부터 아까 말한 그 픽셀 26개 비교하는 거 하고 그렇게 하는 거예요. 아까 비주얼라이즈 한 검정색 이런 것들이 이제 이거 파란색이고요. 그리고 이게 비주얼라이즈 된 DOG 이미지고, 뭐 쓸 수 있다는 거, 이게 좀 헷갈리는데 이건 어퍼바운드예요. 이게 실제 성능이 아니라 위치 빼고 나머지는, 그러니까 위치가 이거 있잖아요. 이거 빼고 나머지 다 그라운드 트루스 썼다는 거예요. 그래서 어퍼바운드고 이게 실제 성능이고, 어퍼바운드가 실제 성능이고, 그리고 4x4 셀이랑 이런 거는 뭐 외울 필요는 없고 그냥 실험의 결과 기반한 결과라는 거를 알면 되고요. 매칭을 할 때는 이제 제일 가까운 것만 고르면은 잘못될 수가 있어요. 그러니까 어쩌다 운이 좋아서 가까운 걸 수도 있잖아요. 그러니까 세컨 클로시스트까지 고려해서 하면 더 로버스트하게 매칭할 수 있다는 거를 이제 그래프가 보여주는 거고, 뭐 이제 당연한 이거 페일러 케이스는 되게 중요해요. 이게 어떤 알고리즘을 배울 때 이게 되게 좋아 보이는 것만 배우거든요. 근데 이걸 보고 이게 안 될 것 같은 거를 알아내는 능력이 되게 중요해요. 그게 이제 전반적으로 이해를 했다는 거거든요, 이 알고리즘을요. 그래서 글로벌 컨텍스트가 없기 때문에 뭐 비슷하게 보이는 것들 다 똑같이 찾을 거라는 게 페일러 케이스, 당연한 이제 페일러 케이스고, 뭐 요즘에는 이제 세멘틱 매칭도 좀 됐어요. 이레이티도 요즘은 잘 안 하고요, 사람들이. 이거는 뭐 다이노3는 메타에서 나온 건데 보면 알겠지만 이제 고양이라는 걸 알려주지도 않았고, 뭐 아무 정보는 안 줬는데 이미지만 줬는데 이제 알아서 고양이 귀나 같은 바디 파트에 동일한 컬러 코드가 있다는 걸 봐서 고양이나 뭐 다른 것도 마찬가지예요. 그거의 스트럭처를 이해하고 있다는 거라서 굉장히 재밌고 서프라이징한 워크라고 생각합니다. 어쨌든 여기까지고. Okay, let's finish. Check the attendance and finish the class. Okay, you can put this number. Thank you.